measure transportation indeed provides a concept of ranks and signs, which enjoys all the properties all the properties that make the univariate ranks successful for statistical inference. Now, I will not go much into the finesse of measure transportation. I will rather emphasize the application of measure transportation and this concept of measure transportation based ranks and signs in the very important and central problem of inference for multiple output regression, MANOVA being kind of a special case. So to start with, I would like to convince you that rank-based inference is not just an anecdotal subject, and that quite on the contrary, it's something more important than you may think. So why would we use rank tests when everybody is typically very satisfied with the asymptotically valid pseudo-Gaussian methods that are available for setting and that are part of daily practice actually? Everybody is using pseudo-Gaussian methods. Well, the reasons are twofold. The reason is twofold. There's a problem with pseudo-Gaussian tests. There's a problem with their validity, one, and there's a problem with their performance. As for validity, well, we know that pseudo-Gaussian tests are asymptotically valid under a very general, a very broad range of non-Gaussian densities. And the problem is actually that this validity, this asymptotic validity, is far from uniform. The convergence to the asymptotic distributions of rank-based statistics very much depends on the underlying densities. And in a semi-parametric model where the parameter of interest, call it theta, and the underlying noise has an unspecified density f, f ranging in some broad class capital F of densities, well, if you look at a sequence of tests phi n for some null hypothesis of the form theta equal to some theta naught, well, the sequence of tests has asymptotic level alpha if and only if the limit as n goes to infinity of the soup over f of the probability of rejecting the null hypothesis is less than or equal to alpha. This is the definition of a size alpha, asymptotic size alpha test. The problem is that pseudo-Gaussian tests, call them phi sub g, they only satisfy the pointwise asymptotic condition that the limit of this probability of rejection is less than or equal to alpha for all f. And there's a problem there due to the non-uniformity of this asymptotic validity, because typically you will have that the lim as n goes to infinity of the soup will be equal to 1. And so you cannot trust the validity of your pseudo-Gaussian test when the underlying density is not specified. This is about validity. But about performance, also there are problems, because the performance of pseudo-Gaussian tests, of course, they are very good in the vicinity of Gaussian densities. But as you move away from Gaussian conditions, that performance deteriorates very fastly. And to convince you about this, let me show you an example and illustrate this with the case of Hotteling's bivariate two-sample test. These problems of pseudo-Gaussian tests indeed are more and more severe as the dimension increases. So here I'm starting with dimension 2 instead of dimension 1. So let us look at Hotteling test under a skew Gaussian distribution where we have location 0, correlation rho, and skewness parameter of the form A, so it's the skewness that acts on the distribution along the main diagonal. Okay. Let me show you some results. And here is in the left-hand panel, you have the power of throttling for a sample of, I think it's, throttling is a two-sample test. So N1 and N2 both are equal to 100, which is a reasonable sample size. And this power is taken under a skew normal distribution where the shift, so the shift in the alternative, delta, null is that delta is equal to 0, and the alternative is that delta is, in this case, larger than strictly positive. And we look at the power of this throttling test. Well, no, I made a mistake. Okay. This should be the pointer, but I don't see it. Or maybe is it this? Well, it's not a problem. So if you look at the left-hand panel, so this is the power. And the power for various values of the skewness parameter. So when A is equal to 0, you have the upper yes, now I have it. So when there's no skewness, you have a Gaussian distribution. This is the power curve plane. But as A increases, so as skewness increases, for A equal to, you have this blue line here. Then you have the red line and the green one. So for A equal to 10, basically the test has no power at all. So this is a problem. You cannot trust the performance of a pseudo-Gaussian test if you are away from a almost Gaussian situation. And the left-hand panel shows you also for a variety of value of the skewness parameter, how erratic the actual size of the test is. So the horizontal line there is a 5% nominal level, and you can see the empirical level for various values here of the correlation coefficient rho as a function of the skewness. So beware of pseudo-Gaussian tests. So this demonstrates two things: the dramatic deterioration of power as you are moving away from the Gaussian, and the erratic behavior of the size when you have various values of the correlation and the skewness parameters. And, well, rank tests, in this case, because we are in a bivariate situation, rank tests are a solution to this problem because they will be distribution free, and hence at least the size will not suffer from the same validity problems. And moreover, as we shall see, this distribution freeness will not be obtained at the expense of the power. So again, to provide an empirical illustration of this, let us look at the data set, which is its classical data set called the Wisconsin Diagnostic Breast Cancer data set. And this data set contains records on a large number of patients, 569, from two groups, benign or malignant tumors. And for each patient, 30 variables have been recorded that can be used for diagnostics, for diagnosis. So those variables, we are labeling them from 1 to 30. And so we are in dimension, it's a data set in dimension 30, okay? But of course, basing a diagnosis on 30 biomedical measurements, this is extremely costly. So the two groups are well separated with those 30 variables, but one may desire to have the same performance in the diagnose based on a smaller number of biomedical measurements. And therefore, we are looking at marginals of this 30-dimensional variables. And we are looking again at bottling tests on the one hand, and the rank-based tests to be defined later. I will define them, don't be afraid, I will go through some definition, but let me show first the performance. And this is a collection of the bivariate scatter plots of this data set. As you can see, just look at the diagonal of this panel where we have the variate histograms. The data are highly skewed, and so they are not really, they are probably not Gaussian. Nevertheless, well, Hotelling is routinely applied to that type of data set. And here is a table of some powers that are obtained for a marginal of dimension 4. Here, so these are the measurements 12, 14, etc., dimension 4, and then 1, 2, 3, 4 marginals of dimension 3. And the tables presents the empirical power of Hotelling of this line, and here the empirical power of the Wilcoxon bivariate rank test that I will describe later on. And well, if you look at the dimension 4, so dimension 4, the Hotelling test is not significant at level alpha equal to 5%, whereas Wilcoxon is highly significant. But there are some marginals of dimension 3 where the contrast is even much more striking, because if you look at this, for instance, Wilcoxon has p-value 0.90, basically 1, whereas Wilcoxon has p-value 0.03. Or here, Hotelling collapses completely with a p-value of 0.21, but the rank-based test is highly significant. So distribution freeness here, which protects you against rejecting the null when you should not, is not obtained at the expense of the power. Okay? I hope that this will convince you that rank-based tests can do something for you, and you should think of using them when you suspect that the underlying data is not Gaussian or maybe severely non-Gaussian. Okay, now let us go to the real thing and the definition of these rank-based tests for multiple output regression. As we all know, rank-based testing methods have been extremely successful in a variety of situations where the observations are univariate. So that means single output regression or univariate linear time series of the ARMA type, or say bivariate independence problems, testing the independence of two univariate random variables. And being distribution free, they don't have this problem of validity. They are valid over the full class of absolutely continuous distributions. And it can be shown that when they are based on adequate scores, and those scores can be data-driven, provided that they are measurable with respect to the order statistic, well, rank tests, as a rule, achieve semi-parametric efficiency. And in regression cases, semi-parametric efficiency means parametric efficiency, since they are adaptive. So extending this to multivariate situation, that is multiple-output regression or MANOVA, of course, is highly desirable. And it has been an open problem on which people have been working for about half a century. And many proposals have been made. Among them, creating marginal ranks, so computing ranks on all marginals of the multivariate output. That's one way. The problem is that the resulting ranks are not even distribution free. They are related to the copula transform, and they are not distribution free. So they are missing their objective. Then there are spatial ranks, and I skip the definition, and they have the same problem that they are not even distribution free. I have a parenthesis here that ranks actually come hand in hand with the concept of quantiles. The quantile region of order tau is the region where containing all the observations with rank, say, less than or equal to some value. So there's a duality between ranks and quantiles, which is very important. And what I'm doing here with measure transportation-based ranks, I could do also finding measure transportation-based quantiles. But quantiles I will not talk about today. So marginal ranks are failing, spatial ranks are failing. There are depth-based ranks, which are distribution-free. They are doing a good job, but they are dropping so much information that they cannot be very powerful. They are dropping all the information since they are based only on the univariate quantity, which is the depth of an observation. They are dropping all directional information. And therefore, unfortunately, they are valid, okay, but they are not very powerful. Then there's the MANOVA ranks and signs that have been mainly exploited in joint papers with Davy Pandaven. They are checking all the boxes, validity, power, everything, but only for the class of elliptically symmetric distributions, which is much better than Gaussian distributions, but still, it's an extraordinary strong assumption. This is this assumption of symmetry, which you would never like to enforce in a univariate case. So why would you like to do it in the multivariate case? It's very unlikely that your data are elliptically symmetric. So at the end of the day, a couple of years ago, that problem was still a very much open problem. And that's when was introduced the idea of using measure transportation into the picture. And this leads to the definition of the so-called Monge-Kantorovich ranks and signs. It's in a paper with Chernozukov, Galichon, and Marc Hallin. And the definition of center outward ranks and signs in a later paper with Spanish Del Barrio and some others. And this is the concept that I will be using here. And contrary to the earlier definitions, the earlier concepts, these ranks and signs do extend to dimension d strictly larger than 1. The essential property of ranks in the univariate case, and that essential property, which is the source of their efficiency and the good job they are doing in statistical inference, is their essential maximal ancillarity property, meaning that they are collecting all the, say, all the information available about the parameter of interest, which is ancillary with respect to the underlying density. Okay, and so what we have is a population definition, which is actually the definition of what we call a center outward distribution function. And we have a sample version where the distribution function is an empirical distribution function, and as we know, an empirical distribution function is characterized by the ranks of the observations. Moreover, if you look at those two concepts, the population concept of a center outward distribution function based on measure transportation, and this empirical distribution function, which is actually the collection of ranks, there's a fundamental Glivenko-Cantelli result showing that the empirical distribution function is converging almost surely and uniformly to its population counterpart. So far, this concept of ranks and signs based on measure transportation has been applied to the construction of distribution tests for a variety of problems, vector independence, multivariate goodness of fit, Varma models, and today I will talk about their application to multiple output regression. Okay, so all the tests we are proposing here are fully distribution free, they are expected to be, and they also achieve semi-parametric efficiency, but in this case, semi-parametric efficiency, the model being adaptive, coincides with parametric efficiency. So they should be good inferential tools for this very central model in statistical inference, which is the regression. So let us go to more precise definitions. So some notation, but I will try to be fast on this because time is probably running. And so we have observations, and they are denoted as, they are actually a triangular array, Z1, Zn, of IID, this is important, d-dimensional random vectors with a distribution P in the family P sub D of, in D families, P sub D of absolutely continuous distributions on Rd, and denote by S sub D the open unit ball in Rd. And denote by U sub D the spherical uniform over the unit ball. So it's a uniform distribution, which is actually, it's not the big uniform distribution in Rd. It's a spherical uniform distribution that is the product of a uniform distribution over the hypersphere and a uniform distribution over the distance 0, 1 to the origin. Okay, and the definition of a center outward distribution function based on a famous result by Robert McCann, which implies the existence of an almost everywhere unique convex lower semi-continuous function, call it with gradient. So it's phi, and it has a gradient nabla phi. So this is the gradient of that phi. And this gradient is pushing P forward to that uniform distribution, meaning that if you compute that gradient at the observation, which has distribution P, then this maps this random vector to a uniform vector taking values in the unit ball. So this is very similar to the probability integral transformation of the traditional distribution function, which pushes the distribution P of a univariate variable forward to the uniform over the interval 0, 1. Then there's a result by Figalli who implies that okay, we denote this as F plus minus. So F plus minus is this gradient of a convex function, which is pushing P forward to the uniform. The idea, of course, is to remind you that it has the properties of a distribution function. And we call this the center outward distribution function P. And since Figali has shown that it is a homeomorphism, it has a well-defined inverse, and this inverse is a quantile function, which we denote as Q plus minus, the center outward quantile function. Okay, now I forward. This is in population now. We have to construct an empirical counterpart to this concept. And the idea is to construct a grid. So in dimension 1, what are you doing to construct your ranks? You grid of over the interval 0, 1 of the form 1 over n, 2 over n, 3 over n, etc. And actually you are mapping your observations in a monotonic way. Monotone means gradient of a convex function to that grid. And this is minimizing, actually, the sum of squared distances traveled. Well, we do exactly the same thing. And we start with factorizing n, the sample size, into a product nr and s. There's a residual here n0. Which is less than the minimum between nr and ns. And r will be the number of rank values, and ns will be the number of sign values, okay? And a grid is constructed, and let me show a picture. So the idea is to have something of this form. This is in dimension 2, of course. So you have ns points over the sphere, which are as uniform as possible over the unit sphere, and then, well, this provided with unit vectors, which are signs, and then you take the intersection of the radii running through ns points with a series of spheres with radii 1 over n r, 2 over nr, 3 over nr, but instead of dividing by nr to remain in the open unit interval, we are dividing by nr plus 1, which doesn't make much of a difference. So this is the definition for the empirical center outward distribution function, and then we have that define the rank of the observation I as the modulus of, well, yeah. So we define the empirical distribution function Fn plus minus as the minimizer of over all possible pairings between the observations and these grid points, the minimizer of the sum of squared Euclidean distances between a point and the grid point it is mapped to. This is a linear program, and there are very efficient algorithms solving this. And this provides us with an empirical distribution function. From this empirical distribution function, we construct ranks by taking the modulus of the empirical distribution function and remultiplying by nr plus 1, so that we have values 1, 2, 3, etc. And then a center outward sign, which is just the unit vector corresponding to this empirical center outward distribution function. So this provides us with ranks and signs. And here is a picture where you see there is no, as usual in measure transportation, there's no analytical form for these quantities, because obtaining analytical forms would mean solving Monge-Ampère partial differential equations, and this is something the analysts still cannot do. And so we recur to numerical solutions. So do people in pure mathematics. And in statistics, well, numerical solutions are what we call simulations. And here is a banana-shaped distribution. Actually, it's a mixture of 3 Gaussians. And this empirical mapping is providing us with the following regions, which are the inverse mappings of the spheres centered at the origin with radii, say, tau. This tau is the radii of the sphere, but in the uniform distribution, it's also the probability content. of that region. So the regions you see here thus are quantile regions, and the probability content of those quantile regions is fixed irrespective, is controlled irrespective of the actual underlying distribution. So they are genuine quantile regions, but they are center outward instead of being ordered from left to right as they are on the real line. So I'm skipping details. Here is another picture where you see those quantile contours. And so the quantile contours are the collection of observations with given rank, okay? And you also have the what we call the sine curves, and the sine curves are the inverse images of the radii in the unit ball form distribution. And well, this is the picture. So let us come back to our problem. We have all those properties for this empirical distribution function and the ranks and the signs. I only would like to stress the Glivenko-Cantelli result here, that the modulus of the difference between the empirical distribution function and the actual one goes to 0 almost surely and uniformly in the observations. So now let us go to, I'm skipping the invariance and equivariance properties, and let us go to our problem, which is the problem of testing the value of a regression coefficients in a multiple output regression context. And the way to proceed is that there's a kind of a technique for constructing this type of tests, and the steps in this method are: one, obtain what we call a Hayek asymptotic representation for the type of statistics we are to use, and second, use this asymptotic representation result in order to reconstruct a rank-based version of the central sequence in a LAN composition expansion of the log likelihood for the problem at hand. So let us start with the asymptotic representation theorem in the Hayek style. This is about statistics of the form of this form. This is just, yes, statistics of this form. So let us denote as T with a tilde under the T. So all quantities with this tilde under the main notation mean they are measurable with respect to the ranks and the signs. So we are in a regression context. There are regression variables, so covariables, and the values of those covariables are here. So these C's here, and they are centered, and so you have a weighted sum here of some score function computed at the empirical distribution function at each observation, okay? And the weights are, of course, the values of the covariates. So this is the type of statistic we will look at. And the problem is that it's a sum of random variables here, of random vectors, which are not independent, because, of course, there's no independence between the values of the ranks and the signs. Of course, this guy here, this empirical distribution function can be expressed in the ranks and the signs. Well, the Hayek asymptotic representation result will provide us with the asymptotic equivalence between this guy and this one, you see the tilde has disappeared. And here we have a sum, but instead of the empirical distribution function, there's the actual distribution function appear here. And these summands here are independent. And so for this guy, central limit behavior is easy to obtain. So if we have asymptotic equivalence between this one, which is rank-based, and this one, well, we have the asymptotic normality of our rank-based quantity. This is what Hayek is calling an approximate score version of the rank-based statistic, and this is what he calls an exact score type rank-based statistic. The difference is that here you have a sum with the score function computed at the various values of the empirical distribution function, and here it's the conditional expectation of the same quantity conditional on the empirical distribution function at the function. So both are measurable with respect to ranks and the signs. And well, we have that indeed these three quantities are asymptotically equivalent in the quadratic mean sense. So the differences are little o of 1 quadratic mean. Okay, when we have this, well, the next step is to look at the LAN representation of the log likelihoods for the model and the study, in this case, the multiple output regression model, and to use the representation theorem in the reverse sense to obtain a reconstruction of the central sequences using the rank-based statistics. This will provide us with a vector of rank-based statistics that will asymptotically recover the optimality properties of the central sequence equivalent to, and actually they are a rank-based version of that central sequence. So I'm skipping details. In this case, well, here is the multiple output regression model, which is, I'm sure, familiar to all of you. Obvious definitions of and notation used in that context. And of course, what we are observing is what we are observing here is the Y's. The Y's, this is what we are observing, and we are also observing the values of the covariates which are in this matrix here. Okay, and the epsilons, of course, are the IID errors which have completely unspecified density. Density there could be absolutely anything, provided that this error is absolutely okay. I'm skipping details, and we know, and it's easy to see, that this model under conditions on the covariates is locally asymptotically normal, and central sequence is its central sequence is so it depends on the gradient of the square root of the density of the error. Well, we have LAN. The next page, next slide. Yes, here we have LAN with a central sequence delta here, which is the vec of this matrix here, which involves, as you can see, these scores, which are the gradients of the square root of the density F. And this is the central sequence, and the information matrix is of this form. I did not define patient, but well, this is not so important here. Now, these were these quantities. This central sequence, for instance, was not based on the ranks. Now, in order to have a rank-based version of the same central sequence, and I'm using the notational trick that there's a tilde under the lambda here, well, we just replace the z's by the rank multiplied by sign. So these are center outward ranks signs we have been building using this grid system I showed you before. And it follows from the asymptotic representation theorem that actually by doing so, I'm constructing something which is a rank-based central sequence. Remember that central sequences always are defined up to a little op quantity, op under, say, the unperturbed value of the. Okay. This, I'm constructing a test statistic, which is usual quadratic form, so there's no surprise here. I'm taking the quadratic form, which is providing the asymptotically optimal test in the Lecam sense, locally asymptotically optimal test, which is a asymptotically maximin test, which is a quadratic form in the central sequence with a matrix, which is the inverse of formation matrix. And if I'm using the rank-based version of the central sequence, well, I have this Q with the under tilde here related to the choice of the scores J. And if this score J is of this form, then I have indeed a reconstruction of the central sequence and the corresponding quadratic form. Right? Of course, this Q sub tilde is distribution free. And so if you are rejecting, it can be shown that this quadratic form under the null hypothesis is asymptotic chi-square, very easy. And since it is distribution free, well, rejecting the null hypothesis when it exceeds the corresponding quantile or the 1 minus alpha of the chi-square distribution, obtain a test which has uniformly over the null hypothesis the asymptotic size alpha. Okay. So that's the technique for constructing tests. Now, if you choose your score J in an adequate way, you can obtain either testing methods which are locally asymptotically maximin at some selected density, or you can go for simple score functions and obtain, for instance, I'm skipping the details, this is the particular case of MANOVA, you can obtain a sign statistic, Q sub sign, by dropping the ranks and keeping only the signs. You can obtain a Wilcoxon statistic here by taking the ranks themselves. So the score function here with respect to the ranks and signs is identity. Or you can go for a van der Waalen or normal score test statistic by using here the quantile function of the chi-square distribution, d degrees of freedom, computed rank divided by nr+1, multiplied sign, and you quadratic form which has this form. Okay, skipping the time is running. And let me show some numerical results. Here I will compare the performance of the Wilcoxon version of test based on the center outward ranks and signs, and the Wilcoxon version of the elliptical or Mahalanobis ranks and signs, so the corresponding one, that's valid only under elliptical densities. And simulations have been conducted. Okay, I'm not going into the details of the simulations. Here are some pictures of the points we obtain in these simulations. We have been looking at mixtures of normals. This is of two normals at U-shaped mixtures. So you see here banana-shaped distribution, S-shaped. So it goes down and then up and down again. This is skew student with 3 degrees of freedom. So these are the type of distributions we have been looking at. And in this, these diagrams, we have been plotting the powers, the empirical powers we are obtaining. And this is for various values of the sample size. So you have 100, 400, 900, meaning 50 and 50. It's about, again, a 2-sample problem. So here we have 50 and 50, 100 and 200, 450, 450. And the plot you have, the solid line is the empirical power of our Wilcoxon tests based on the center outward ranks signs. And the dotted line, which you don't see very clearly here, is the power of Hotelling. Then the dashed line is for these elliptical ranks and signs. And you can see that in the first case, which is the case of a normal distribution, the underlying density is normal, well, there's not much difference. You are performing equally well as Hotelling. So you don't lose anything in that respect. But when you move to a student distribution, here 1 degree of freedom, Cauchy, well, you can see that you are doing much better and certainly than Hotelling, which is here below and has absolutely no power. So it's very close to 0. So on the Cauchy, we still have a good power curve for our method. And as you can see, the validity is not a problem here. We have the size, nominal size is satisfied. So this is a T distribution with 3 degrees of freedom. And again, you can see that Hotelling is performing very badly. And our method is as powerful as the method based on the elliptical ranks and signs, which, however, are exploiting an additional information about the underlying distribution, that it is elliptical, which is the case here indeed. So in the elliptical case, in the Gaussian case, we don't lose any power. In the elliptical case, we don't lose any power with respect to the method based on elliptical ranks and signs. But now, if you are looking at more extreme situations, for instance, the mixture of 2T distributions, which is here, well, you have here power for our method, and then you can see Hotelling is here under the 0.5, the 5% line, failing miserably. So this is for 100. This is for 400. No, this is for 900, excuse me, 400 and 100. And we are doing much better than the elliptical ranks and signs. So there's a gap here between solid line and dashed line. Same conclusions with the U-shaped mixture, the S-shaped mixture. we always have a quite substantial benefit in the power with respect to these other methods. So our method does work and does provide a powerful tool for this situation. All right. Let me go now to another empirical illustration. Definitely the performance of this center-outward rank and sign-based testing method is impressive. And this is about a data set from, it's an archaeological data set, not very large sample. We have 126 measurements of four chemical molecules that had been found in glass vessels excavated at 3 archaeological sites in the Syro-Palestinian region. So, and actually in present-day Israel, but considerations. First site is Apollonia with 54 observations. The second one is Bet Eliezer, and the other one is called Egypt. I don't know whether it goes to the border. And the objective is a detection of possible differences in the techniques for producing those glass vessels based on a measurement of these 3 chemical molecules. Okay? Here is a picture of the bivariate marginals, and again, you can see this is very far from Gaussian. Nobody would dare guessing an underlying Gaussian distribution for such a data set. And the classical test is the Pillai trace test for, so this is a MANOVA problem. Perform the Pillai trace test. And then we have performed two tests based on the center-outward ranks and signs. Test 1 with factorization to NR equal to 7 and S equal to 18. And the second one, the converse, NR equal 18 and S equal to 7. And as you can see, the differences in the powers, so these are the p-values, the differences in the p-values are just striking. For instance, using our rank test here and looking at those 2 chemical quantities here, here we have, so this is for the bivariate marginals of the data set. Here we have p-values of 0, whereas the Pillai trace test has p-value of 0.12. Same here, 0.14 for Pillai, value 0 for our rank-based value 14, 0.14. And so our tests do detect very, very significantly difference between the techniques for producing those glass vessels, whereas the traditional method does not. We also have conducted the same analysis for the full 4-dimensional data set. Pillai's test fails to detect any difference. P-value is 0.15, and we have a p-value which is basically 0. It's 10 to the minus 15. So, okay. And notice that since the observations are highly non-elliptical, as see on the scatter plots, well, the elliptical Wilcoxon rank tests, elliptical ranks and signs, also fails to detect anything. So definitely the measure transportation-based ranks and signs do a much better job in such a situation. So conclusions, classical multivariate analysis methods, which are the daily bread and butter of us. Of course, this is not high dimensional, this is not time series, it's basic model, but it's also perhaps the most widely used model. MANOVA is something quite important in daily practice. So daily practice remains deeply marked by Gaussian or elliptical assumptions, and based on these methods, I think I have convinced you that one can do much better by using more reliable, but also more powerful rank-based techniques. For those who are interested, here are some references. These are papers on the concepts. So there's the paper with Shonozukov, Galichon, and Henri. And this is the paper with Del Barrio, Cuesta Albertos, and Carlos Matran, both annals years. This is that paper by Figali, which was quite instrumental in showing that the optimal transport or the gradient of convex function we are using is a homeomorphic, so that it can be inverted. And there's a non-technical survey here that has appeared in the Review for Statistics and in that application last year. Then our applications, rank tests, and R estimation. Here for Varma models in time series. This is for testing for VAR models, so autoregressive, vector autoregressive. This is the paper on which this talk has been based with my colleagues from Prague. And this is about testing for vector independence, distribution-free, rank-based version of Shekeli's distance covariance quantities. So I thank you very much for your attention. Of course, I'm happy to questions you may have.
Thank you very much, Marc, for a very informative, nice talk. So indeed, there is room for questions.
So situation is complicated. So my asymptotic theory is Masanobu, I'd be delighted to develop this, but this is notoriously difficult, and you are the world expert in those higher order efficiency problems. So I'd be delighted to collaborate with you on that topic. But you are perfectly right. You are perfectly right. Now, I have objections against the likelihood ratio test, which the optimality is not clear. It depends on the model. Yeah. Whereas the quadratic forms based on LAN, they are asymptotically optimal in any LAN model. And they have the form of a Lagrange or Lagrange multiplier structure, whereas likelihood ratio tests involve something, estimation under contiguous alternatives, which is
other questions from the audience?
It's very interesting. So do we have some idea?
Well, it's very clear that since we are aiming at quote-unquote universal validity, we do not escape the curse of dimension. So as D increases, I mean, n observations in dimension D is kind of the same story as root D n observations in dimension 1. And so, well, it would be nice to have an answer at such questions, but type of answer I can think of is not very, what can we say exactly? As D increases, larger and larger samples are required to attain same type of performance. That's very clear.
You also have assumptions on density and so on, and how those assumptions influence the observation.
Okay, well, probably the skewer the underlying density, the worse the approximation. No, because we are having rank-based, they are distribution-free. So I have no answer, but at least the approximation is uniform. It does not depend on the actual underlying density. I can't say much more. I have no result about that. In the univariate case, there are results on the Berriesine convergence, but certainly not at this stage measure transport. And note that this is not about asymptotic normality of the value of center outward distribution function computed at some observation. It's about the asymptotic normality of rank statistics with adequate score functions. As we know, the asymptotics of the measure transportation itself quite delicate. There's the problem of the bias, and there's much work going on this. I don't think we are.
Okay, I myself was also wondering, so I found this comparison between your tests and the tests based on elliptical symmetry very interesting. I was wondering, do you also have results in terms of asymptotic relative efficiencies for this comparison? That was one question, because in particular, I was surprised to see that that these tests did better under student 1. And I think in simulations you got better results there. So I was wondering how come that they could get distributions under assumption.
They won't be the method under elliptical distributions if you are using elliptical scores. Then they will be asymptotically equivalent. Now, all those results about asymptotic relative Savage, Hodges, Lemon, Bound, etc., have been obtained by Bodisen, but for subfamilies of density, elliptical subfamily or the dependent component subfamily. So these are not really what we would like to see. We would like to see Chernow-Savage for the whole family of, and that is still an open question. Nobody has.
Okay, thank you very much. So if there are no further questions, then I would say we thank the speaker again.